Example 2 for 10.3 wants us to start to look at function compositions as, the actual functions. So looking at domain and range, and, we're going to talk about the graphs in this as well. And I think in order to do this as best as we can, we really should have the graphs of f of x and g of x. Fortunately, though, we've spent, 10 chapters talking about how to draw these graphs without necessarily resorting to technology each and every time. So f of x is equal to the square root of x minus 1, which is the graph of y equals the square root of x moved 1 unit to the right. And so that's going to look something like this, where that point right there is at 1 comma 0. That's going to matter for our domain. I'm just going to clean this guy up a little bit. G of x is probably the equation that most students are comfortable with. It's equal to x squared. That's our standard parabola that's opening up. And maybe I'll draw that a little bit better. I'm sure I could. So g of x is equal to x squared. And what that graph would look like is something like this. So I'm going to immediately do domain and range for these as well. The domain for f of x is going to be that x must be greater than or equal to 1, but is an element to the real. Something just a little bit kind of clustered on the left side there. So x is greater than or equal to 1, and it's an element to the real. And then the range is going to be y is greater than or equal to 0, and y is an element to the real. For g of x is equal to x squared, we are simply going to have x as an element to the real, but then my range is also going to be y is greater than or equal to 0, and y is an element to the real. Hopefully that there's no real problem with those. You've certainly spent a fair amount of time figuring that out throughout the course. We also, though, are asked to determine f of g of x and g of f of x. And I want to make sure we identify how to read that. That's f open dot g of x. I'm just going to write that is f of g of x. I actually prefer when the function is inside a bracket like that. So function f with g of x in place is going to be, and this is really important, that I'm going to take function f, which is the square root of x minus 1, but instead of x, it's function g, which is x squared. So f of g of x is the square root of x squared minus 1. And I'll write that just a little bit cleaner down here. So that's the square root of x squared minus 1. All right, while I'm at it, I would like to do my g of f of x function, sorry. So that is written as g open dot f of x, and I'm going to write it the other way as well. That's g of f of x. And what that's going to look like, and this is going to be really important, that some simplifications can be made when we're working through these, but you have to be really careful with that. When you are trying to, evaluate whether you can do a substitution or not, you have to be really careful with whether you're kind of eliminating some of the information that's given to us. And the reason why I bring that up is g of f of x is g of x is something squared, and f of x is the square root of x minus 1. Now, I'm on board with the idea that the square root and the squared symbol cancel each other out. That's true, but what's really important is that we don't lose the original information that x minus 1 was inside of a radical. And really what I'm getting at is that when I look at the domain and range of these functions, the domain of g of f of x, because f of x is that inner piece, I am still going to have to say that x is greater than or equal to 1, and x is an element to the real. Because if x is less than 1, even though we're squaring it, you cannot take that square root of a negative. And that's a confusing concept for a lot of students, that if the inner function has some invalid inputs, then the composition of that function will have those same invalid inputs. Now that creates a pretty strange graph for g of x, because certainly the square root and the squared would cancel, but what's going to happen is that we are going to have 1 comma 0 right there, and then it's just going to be that linear line, which is going to look a lot like x minus 1. It is x minus 1, but the function doesn't exist to the left of x is equal to 1. And that means that our range is also y is greater than or equal to 0, and y is an element to the real. Now, on the other side here, this f of g of x, I think it's a little bit trickier to draw the graph of it. Just let me rewrite what it is. So this is f of g of x. I think the best way of looking at this is that we are taking the square root of the function x squared minus 1. Now, the reason I bring it up like that is because we spent time in chapter 2 talking about how to take the square root of functions. So just bear with me here. There's going to be a little bit of extra writing on this one. We are going to have this red graph, which I'm just going to write beside, is x squared minus 1, and then I'm going to take the square root of that. If I take the square root of that function, my square root is going to look something like this, where it is invariant, where the function is 0 or positive 1. So there's 4 invariant points, and the function doesn't exist where it would cause us to take the square root of a negative. Now I'm going to get rid of that red graph now just so we can see what's happening. That's what my green graph would look like. And the reason for that is if x is anything in between +1 or -1, so 0 or 0.5 or -0.2, then we end up taking the square root of a negative. And so we get some domain restrictions in there. And understanding where those domain restrictions come from is really important. There's another way to find them. It's the idea that the radicand, x squared minus 1, must be greater than or equal to 0. That occurs when x squared is greater than or equal to 1. And that occurs when x is greater than or equal to 1 or less than or equal to -1. Now, if you want to know where those points occur, this is 1, 0. That's -1, 0. So I'm going to put that domain and range in red here. We would say that for x must exist, and you can do this with inequalities, there's nothing wrong with that x has to be less than or equal to -1, but greater than or equal to +1, and it's any real number outside of the, satisfying that restriction. The range is that y must be greater than or equal to 0, and y is an element to the real. That's not really the focus for this example. The real focus in this example is the idea that even though this blue graph would look like x minus 1, because the square root cancels with the squared, because of where that composition came from, the overall function or the resulting function still has the restrictions that the inner function would have. And it's why I actually wouldn't recommend writing this simplified version, because if you put into your calculator y equals x minus 1, that line is going to have a domain of all real numbers. But if you put into your calculator what I've written there, let's do that. We have a minute here. So if we grab our calculator and we put in for y equals, I'm going to put in a bracket the square root of x minus 1. And then outside of that whole bracket, I'm going to square it. When I graph it, the calculator shows me that it doesn't actually exist when x is less than +1. And I want to show you the difference. If I tell my calculator, oh, just draw x minus 1, nothing wrong with that, it is going to fill in this bottom section. And that bottom section isn't actually valid, because if I pick x is -4, I would have -4 minus 1, which is -5. I can't take the square root of that. So it doesn't exist in my composite function.